All right, so we're going to pick up here by taking a look at example number 3. Determine with justification whether this series converges or diverges. Now here I'm going to point out one of the most important things that you can begin to highlight for what to do when we're looking at this comparison test that's new and this limit comparison test. Because a lot of times people struggle to understand when we would use either of these. And this is going to be really key. I'd like us just really quickly to focus on something, even though it's not going to ultimately be like our final work for this problem. I want you to just consider the following. I'll erase it in a second, so don't bother writing it down. But take a look at the idea here of using the comparison theorem. If I wanted to use the comparison theorem here, not limit comparison, just regular comparison, I might notice something. Again, I might be able to see that if I just got rid of that -1, I could get to something that looks pretty simple. Again, I can get to something that looks like it's going to be geometric. And that's great. I can know if this thing converges or diverges. We actually looked at this in the last couple videos. We said that this total series would, if this was a series here, it would converge to the value of 1. But notice that I still have to decide on what inequality symbol to put in between over here. Since this denominator has something being taken away from it, it should be smaller. And therefore, it creates a bigger overall fraction. But now notice a dilemma. I now have something that is convergent on the small side, and on the other side, I don't know anything yet. Can I use the comparison theorem to help me? The answer here should be no. Because if the small thing is convergent, that doesn't tell me anything about the big thing. So I have a big dilemma. This inequality symbol right here is facing the correct direction, but it is facing an inconvenient direction for my goals. If it was only the case that that inequality sign could be flipped, then I would have found a big thing convergent and I would have known the small things convergent. But since I don't have that inequality facing in the appropriate direction, this is a perfect time. It is the exact time that you would attempt to use limit comparison test. I can go ahead and state the following. I'll erase the work below in just a moment. So I'll start up here by just saying, consider the series 1 over 2 to the n. Again, I know this is equal to the series 1/2 to the n minus 1, which is a convergent geometric series. Okay, so I still am going to be working with this, but notice, since I know the inequality is not going to work out, I can kind of almost erase all of this scratch work. I don't need it. And I can just go right to the limit comparison, which would say I'm going to take my original series and the one I started with, and I'm going to divide them. I don't care which one goes on top or on bottom. It's not really relevant. But I'm going to go ahead and just start by setting up a ratio after I go ahead and check to make sure that both series have positive terms. Okay, so I can see here that both series very clearly contain only positive terms. That's pretty obvious. No big mystery there. But once I've done that, I can then say that we calculate, and I'm going to set up my limit. Again, it doesn't matter which order you go. Sometimes you'll see that setting up a limit in one direction is going to be convenient, and another direction might be less convenient. Well, you just have to experiment and figure out what works well and what doesn't. Here, I'm going to go ahead and I'm going to go and put my 1 over 2n minus 1 in the denominator, my 1 over 2 to the n in the numerator. Now, when I attempt to simplify this down, I'm going to notice some things. First, if I multiply by the reciprocal, I'm going to end up with something like this. And from here, I'm going to just use some cool algebra moves. I'm going to separate this into 2 to the n over 2 to the n minus 1 over 2 to the n. Of course, that means this is a limit of 1 minus 1 over 2 to the n. And can you guess what the limit's going to be? Well, it should be 1 minus 0, which is 1. Okay, so this is really good news. Notice, this doesn't tell me at all what either of these series converge to or if they converge in and of itself. What this tells me is that since I now have a value of 1, and that is positive and finite, we know both series converge or both diverge. Notice the limit comparison test doesn't give us a final conclusion yet. It's why it's always going to be so important that the series that we use with our original is something that we know something about. But this series, we already said, is a convergent geometric series. So if this one converges, then I can clearly say, so by the limit comparison test, which you'll often see me abbreviate as LCT. In fact, right now, I'm going to go over to our nice little sheet, and I'll even put that right here, LCT. By that limit comparison test, the series 1 over 2 to the n minus 1 converges. This is a very important thing to understand, that again, I can use this limit comparison at the moment that I'm trying a regular comparison and I find the inequality just isn't working. But it's also imperative that I make sure that the series that I'm choosing to compare with is something that I know something about. All right, we'll take a look at example number 4 in the next video.